Welcome to our deep dive into severe weather systems. Today, we are going to explore the incredible power of thunderstorms, tornadoes, and the early stages of tropical cyclones. Let's start with the basics. A thunderstorm is a violent, short-lived, and highly localized weather event. They are driven by rapid convection, which is the intense upward movement of warm air. For a thunderstorm to form, you need two main ingredients: high temperatures and plenty of humidity. This is why they are less common over cooler water bodies, and they are incredibly common globally. There are roughly 16 million thunderstorms every year, meaning right now, as we speak, there are about 2,000 happening around the world. The life cycle of a thermal thunderstorm begins with the cumulus stage. During a hot summer day, the ground heats up intensely. This heat transfers to the humid air just above it, causing that air parcel to rapidly rise. As this air rises, it creates a localized area of low pressure near the ground. To fill this void, surrounding air rushes in, fueling a continuous, intense convection cycle that builds a towering cumulonimbus cloud. Next is the mature stage, where the storm reaches its peak. As the rising moisture condenses, it releases latent heat. This extra heat makes the air even lighter, accelerating the updraft and pushing the cloud to massive heights. Eventually, the cloud hits the stable stratosphere and flattens out, forming a characteristic anvil shape. Meanwhile, the heavy moisture falls, dragging cool air down with it. This intense downdraft is what causes these sudden, violent gusts of cool wind and heavy rain you feel just before a storm hits. Once formed, how does a thunderstorm move? Interestingly, their paths can be quite erratic. Their movement isn't just pushed by high-altitude winds. It is heavily influenced by the internal interactions of their own updrafts and downdrafts. A typical isolated storm moves at a leisurely 20 kilometers per hour. However, in extreme cases, massive, highly organized storms known as supercells can race across the landscape at speeds up to 80 kilometers per hour. We mentioned downdrafts earlier, but sometimes these downward rushes of cold air are incredibly violent. We call these downbursts. A macroburst is a massive downdraft over 4 kilometers wide, packing winds up to 215 kilometers per hour. A microburst is smaller in size, but even more concentrated and deadly, with winds reaching 270 kilometers per hour. Because they cause sudden, massive changes in wind speed and direction, microbursts are exceptionally hazardous to airplanes, especially when they are taking off or landing. Finally, the storm enters the dissipating stage. The cloud has grown so tall that it reaches altitudes with sub-zero temperatures, allowing hailstones to form. At this point, the massive amount of falling rain and hail creates overwhelming downdrafts. These downdrafts effectively choke off the supply of warm, rising air that was fueling the storm. Without that warm updraft, the storm quickly starves. After a brief period of intense precipitation, the storm dissipates in just a matter of minutes, leaving clear skies behind. Not all thunderstorms are created equal. While we have looked at the general formation, meteorologists categorize them based on their triggers and organization. We have convectional, frontal, and orographic storms based on how the air is lifted. But looking at their internal structure, we classify them into single-cell, multi-cell, and supercell thunderstorms. Let's break down these structural types. A single-cell thunderstorm, also known as an isolated thermal thunderstorm, is the most basic type. These are small, relatively weak storms that pop up on hot summer afternoons, driven entirely by local surface heating. They live fast and die young, usually completing their entire life cycle within an hour. While brief, they can drop heavy rain and lightning. In India, these pre-monsoon summer storms are quite famous. They're affectionately called mango showers in Kerala and blossom showers in Karnataka because they help ripen the local crops. Stepping up in complexity, we have the multi-cell thunderstorm. Instead of just one isolated updraft, this system sustains itself by constantly generating new cells. As rain-cold air from an existing cell hits the ground and spreads out, it creates a gust front. This cold front acts like a wedge, forcing warm surface air up to create brand new updrafts. While each individual cell might only last 30 to 60 minutes, the system as a whole can march across the landscape for hours, bringing continuous threats of hail, flooding, and strong winds. The undisputed king of thunderstorms is the supercell. What sets a supercell apart is its incredible organization and longevity, easily lasting well over an hour. The defining feature of a supercell is its updraft. Unlike normal storms, where the updraft goes straight up and gets choked by its own rain, a supercell's updraft is tilted and rotating. This separation of updraft and downdraft allows the storm to feed itself continuously. Because of this intense rotating energy, supercells are the birthplace of the most large and violent tornadoes on Earth. Deep inside that supercell is a structure called a mesocyclone. A mesocyclone is essentially a massive, rotating vortex of air suspended mid-air within the thunderstorm. It acts as the engine of the supercell, spinning furiously as warm air is drawn upward. While not every mesocyclone will produce a tornado, this mid-level rotation is the critical precursor. When conditions are just right, this rotation can tighten and extend toward the ground. And that brings us to tornadoes, often called twisters. A tornado is a small diameter, violently whirling vortex of air that is in contact with both the ground and the convective cloud above. Do not let their relatively small size fool you. Tornadoes generate the absolute strongest winds known on our planet, reaching terrifying speeds of up to 500 kilometers per hour. They most commonly occur in the mid-latitudes during spring and summer, where warm tropical air frequently collides with cold polar air. The birth of a tornado is called tornadogenesis, and it requires a very specific sequence of events. It starts with vertical wind shear, which is winds blowing at different speeds and directions at different altitudes. This shear creates an invisible horizontal tube of spinning air near the surface. When a powerful thunderstorm updraft develops, it grabs this horizontal spinning tube and tilts it completely vertical, creating our mesocyclone. Finally, the storm's downdraft, fueled by condensing rain, pushes this tightly rotating column of air down until it makes contact with the ground, officially becoming a tornado. When a tornado forms over a body of water, it is called a waterspout. Like land tornadoes, they are connected to a towering cumulonimbus cloud above. However, there is a common misconception about them. Despite their appearance, most waterspouts do not actually suck up a massive column of seawater. The visible funnel is mostly just condensed water vapor, exactly like a cloud. Generally, waterspouts are much smaller and weaker than their land-based counterparts, though they still pose a severe threat to boats. Where do these violent storms happen? Tornadoes are overwhelmingly a phenomenon of the temperate regions. While they have been reported on every continent except Antarctica, the geography of the United States makes it the undisputed tornado capital of the world, hosting the most frequent and violent twisters. Canada comes in second. Over in the Indian subcontinent, the unique topography and clash of air masses make Bangladesh the country most prone to devastating tornadoes. Let's shift our focus to the electric light show of a thunderstorm, lightning. As water vapor rises high into the freezing levels of a cumulonimbus cloud, it forms ice crystals. Updrafts push small crystals up, while gravity pulls larger, heavier crystals down. They crash into each other constantly. These collisions literally knock electrons off the atoms, a process called ionization. The lighter, positively charged ions, or cations, get swept to the top of the cloud, while the negatively charged electrons, or anions, gather at the middle and bottom. This separation of charges creates a massive electrical potential difference between the top and bottom of the cloud. We are talking billions of volts. Eventually, the insulating capacity of the air completely breaks down. In a fraction of a second, a massive current of hundreds of thousands of amperes surges between the layers to neutralize the charge. This incredible flow of electricity heats the surrounding air column to extreme temperatures, turning it into glowing plasma, which is the brilliant flash of lightning we see. And where there is lightning, there is thunder. That massive electrical discharge heats the air channel to an astonishing 30,000 degrees Celsius, which is 5 times hotter than the surface of the sun. This extreme, instantaneous heating causes the air pressure to spike, forcing the air channel to expand outward at supersonic speeds. This creates a violent shockwave. As that shockwave travels outward and slows down to the speed of sound, it decays into the deep acoustic rumble or sharp crack that we hear as thunder. While most lightning stays within the clouds, about 20 to 25% strikes the ground. The Earth is generally electrically neutral, but the massive negative charge at the bottom of the cloud repels electrons in the ground, leaving the Earth's surface positively charged. The electrons in the cloud desperately want to connect with that positive ground. Because air is a terrible conductor of electricity, the lightning bolt will actively seek out the shortest path and the best conductors available, which is exactly why it tends to strike tall trees, metal poles, and skyscrapers. Lightning is a serious hazard. Globally, the most lightning-struck place on Earth is Lake Maracaibo in Venezuela, where warm waters and surrounding mountains fuel endless storms. In India, lightning deaths are rising, particularly near the Himalayas and in Bihar during the pre-monsoon season. Interestingly, direct hits on humans are rare. Most fatalities occur from ground currents. When lightning strikes a tree, the massive electrical energy spreads laterally across the wet ground, electrocuting anyone standing nearby. This is why you should never seek shelter under a tree during a storm. Another destructive element of severe thunderstorms is hail. Hail is a form of solid precipitation consisting of frozen pellets or lumps of ice. If you were to cut a large hailstone in half, you would see it looks a bit like an onion, made up of alternating layers of clear, translucent ice and thin, white, opaque ice. While almost all thunderstorms produce hail high up in the clouds, we only call it a hailstorm if those ice pellets actually survive the fall and reach the ground without melting. So, what exactly does a storm need to produce hail? It requires a very specific recipe. First, you need a violently strong updraft to keep heavy ice suspended in the air. Second, the cloud must have a high liquid water content to provide material for the ice to grow. Third, the cumulonimbus cloud must have great vertical extent, reaching high into the freezing layers of the atmosphere. And finally, you need high surface temperatures. This might seem counterintuitive, but that intense surface heat is what drives the powerful updrafts required to hold the hail aloft. The formation process is a wild ride. It starts as a water droplet that freezes onto a dust particle. The storm's massive updrafts, blowing it up to 180 kilometers per hour, blasts this tiny ice pellet high into the freezing cloud. Here, it collides with super-cooled water droplets that instantly freeze onto it, adding a new layer. The hailstone might fall slightly, catch another updraft, and get blasted back up, adding layer after layer. It only falls to Earth when it becomes too heady for the updraft to support. Interestingly, despite having many thunderstorms, hail is rare in the tropics because the atmosphere there is too warm at higher altitudes, melting the ice before it hits the ground. To summarize the destructive potential of these systems, thunderstorms pose multiple severe hazards. The intense, concentrated rainfall can lead to sudden and devastating flash floods, often referred to as cloudbursts. Lightning strikes cause fatalities and ignite massive wildfires. Hail can decimate agricultural crops in minutes and destroy property. The straight-line winds and downbursts can knock down power lines and pose lethal threats to aviation. And of course, the tornadoes spawned by supercells can obliterate human-made structures. There is a terrifying phenomenon where wildfires actually create their own thunderstorms, known as pyrocumulonimbus clouds. The intense heat from a massive forest fire causes air to rise incredibly fast, drawing in surrounding air and forming a towering smoke plume. As this plume reaches the freezing upper atmosphere, ice particles form and collide, generating lightning. This lightning strikes the dry ground, igniting brand new fires miles away. Furthermore, the massive updrafts create powerful winds that fan the flames, making the original fire burn hotter and spread faster, as seen in recent severe fires in Australia and California. Now, let's transition from localized thunderstorms to massive oceanic weather systems, tropical cyclones. A critical concept here is vertical wind shear, which is the difference in wind speed and direction at different altitudes. For a tropical cyclone to develop, vertical wind shear must be very low. If the winds at the top of the atmosphere are blowing much faster than at the surface, they will literally decapitate the growing cumulonimbus clouds, destroying the storm structure. Because high wind shear dominates the temperate regions, the birth of tropical cyclones is strictly confined to the deep tropics, where the shear is weak. You might wonder why India doesn't see massive tropical cyclones during the peak of the southwest monsoon. The answer is twofold. First, the monsoon creates massive vertical wind shear. You have strong westerly winds near the surface and powerful easterly winds high up in the troposphere. This rips developing storms apart. Second, the only zone where storms can try to form is the far North Bay of Bengal. Because this body of water is so narrow, any low-pressure system that forms hits land in just a day or two. They simply don't have enough time over the warm water to intensify into a full cyclone. So how do they actually form? Tropical cyclones have a thermal origin, meaning they are powered entirely by heat. They develop over warm tropical oceans, primarily in late summer when the water is at its absolute hottest. Under these perfect low shear conditions, a fascinating process occurs. Multiple individual thunderstorms begin to cluster and merge together. As their powerful convectional currents combine, they pull massive amounts of air upward, creating a broad, intense low-pressure system at the ocean surface. This merging of thunderstorms is the crucial first step, setting the stage for a massive cyclone to begin spinning up. Tropical cyclones are rapidly rotating violent storms that originate over tropical oceans, typically in late summer. They are characterized by a closed, low-pressure center with steep pressure gradients, which drive the intense wind speeds. They feature a closed, low-level cyclonic circulation caused by the rapid upward movement of hot, moist air subjected to the Coriolis force. You will also see strong squalls and a spiral arrangement of thunderstorms producing torrential rainfall. For a tropical cyclone to form, several specific conditions must be met. First, a large sea surface with a temperature higher than 27 degrees Celsius is needed to provide abundant moisture and latent heat. Second, there must be enough Coriolis force to create a cyclonic vortex. Third, a pre-existing weak low-pressure area or low-level cyclonic circulation must be present. Finally, no vertical wind shear and upper-level divergence are required to allow the storm to grow vertically without being torn apart. Why do tropical cyclones mostly form on the western margins of oceans? This is due to warm ocean currents driven by easterly trade winds, which drag warm water westward, creating a thick layer of water above 27 degrees Celsius. Conversely, cyclones are very rare on the eastern margins of oceans because cold currents lower the surface temperatures, making them unfit for cyclonic storms. An exception occurs during strong El Niño years, when warm waters accumulate in the eastern Pacific, allowing hurricanes to form there. When a tropical cyclone makes landfall, it rapidly weakens and eventually dissipates. This happens because the storm is cut off from its primary energy source, the warm ocean water. Without an adequate supply of moisture, the storm is deprived of the latent heat of condensation that drives its massive convective engine. As the cycle of rising humid air and condensation breaks down, the storm loses its intensity. The Coriolis force is essential for giving the cyclone its spin. At the equator, the Coriolis force is zero, which is why cyclones do not form exactly on the equator. However, as you move away from the equator, the force increases. By the time you reach about 5 degrees of latitude, the Coriolis force becomes significant enough to deflect the rushing air and create the swirling cyclonic vortex necessary for a storm to develop. In the northern hemisphere, cyclones occur mostly in late summer, particularly around August. This is because water has a high specific heat capacity, meaning it takes a long time to warm up. While land masses peak in temperature around June or July, the oceans do not reach their maximum temperatures until August. Additionally, during this time, the Intertropical Convergence Zone, or ITCZ, is farthest from the equator, meaning the Coriolis force is stronger and more capable of enhancing the cyclonic vortex. The birthplace for many tropical cyclones is a low-level disturbance. This is essentially a low-pressure trough associated with extensive cloud formation and thunderstorms that moved from east to west within the ITZZ. These easterly wave disturbances act as the seedling circulations for cyclones. While they are just persistent groups of thunderstorms traveling together under the influence of trade winds, under the right conditions, they can intensify into full-blown cyclones. Looking at the North Indian Ocean, the Bay of Bengal experiences significantly more cyclones than the Arabian Sea, with a ratio of about 4-to-1. Why is this? Cyclones in the Bay of Bengal either develop in situ or are remnants of typhoons from the Northwest Pacific that travel across the South China Sea. Since the Pacific produces a huge number of typhoons, the Bay of Bengal gets a high quota of these remnant storms. In contrast, storms in the Bay of Bengal usually weaken over India, so few migrate into the Arabian Sea. Temperature and evaporation also play a role in this regional difference. The surface temperature in the Bay of Bengal is generally higher than in the Arabian Sea, which is cooled by monsoon winds. Furthermore, while monsoon winds increase evaporation over the Arabian Sea, they constantly drive that moisture away towards the Indian landmass. The rate of evaporation is controlled by the vapor pressure of water, which increases with higher temperatures and lower air pressure, fueling storm development more effectively in the Bay of Bengal. Another crucial factor is water salinity and stratification. The Bay of Bengal receives massive amounts of fresh water from major rivers like the Ganga and Brahmaputra. This less dense fresh water forms a layer on top, creating high stratification and inhibiting vertical mixing with cooler, deeper waters. This keeps the surface very warm. The Arabian Sea, however, has high evaporation and low freshwater inflow, making its surface water saltier and denser. This promotes vertical mixing, which brings cooler water to the surface and suppresses cyclone formation. For a low-level disturbance to grow into a violent tropical storm, there must be instability in the atmosphere. This instability is often caused by the convergence of air masses with different temperatures. When trade winds from both hemispheres meet along the ITCZ, especially when the ITCZ is farthest from the equator, the temperature contrast between these air masses create the necessary conditions for a low-pressure cell to intensify into a depression. Upper air disturbances also heavily influence tropical cyclones. Remnants of upper tropospheric westerly troughs can move deep into tropical latitudes. Because divergence occurs on the eastern side of these troughs, it forces air at the surface to rise, assisting in the birth or intensification of a cyclone. However, the speed of these troughs matters. Fast-moving troughs create high vertical wind shear, which tears storms apart. Slow-moving troughs, on the other hand, can steer tropical cyclones eastward or northeastward. The development of a tropical cyclone, known as convective cyclogenesis, happens in stages. Stage 1 is a tropical disturbance, where multiple thunderstorms merge to form a persistent weather system. If conditions are right, the Coriolis force gives this system a whirling motion, leading to Stage 2, a tropical depression. At this stage, a closed cyclonic circulation is established, but maximum sustained surface winds remain below 63 kilometers per hour. As the system intensifies, it reaches Stage 3 and becomes a tropical storm. Sustained winds increase to between 63 and 119 kilometers per hour, and the distinctive swirling cyclonic shape becomes highly organized, though an eye is usually not yet present. When sustained winds exceed 119 kilometers per hour, it reaches Stage 4, becoming a full tropical cyclone. At this intense stage, the storm typically develops an eye, a central area of relative calm and the lowest atmospheric pressure. If we look at the vertical structure of a mature tropical cyclone, it is divided into three main layers. The lowest is the inflow layer, extending up to 3 kilometers. This is where warm, moist air spirals inward to drive the storm. The middle layer, from 3 to 7 kilometers, is where the main cyclonic convection and heavy rainfall occur. Finally, the outflow layer sits above 7 kilometers. Here, the air that has risen through the storm diverges outward in an anticyclonic or opposite direction, venting the storm. Let's break down the early mechanism of this cyclogenesis. Warm, moist air over the ocean is uplifted. As it rises and cools, the moisture condenses, releasing latent heat. This heat warms the surrounding air, making it lighter, so it rises even faster. To fill the void left at the surface, fresh, moisture-laden air rushes in from the surroundings. As this incoming air is deflected by the Coriolis force, it begins to spiral, creating a powerful cyclonic vortex. How does the famous eye of the cyclone form? It is a result of incredible physics. The intense low pressure at the center creates massive wind speeds. These high speeds increase the Coriolis deflection, which in turn increases the tangential or centrifugal force pushing outward. When this outward centrifugal force balances the inward centripetal pull of the low pressure, the air is forced to form a cylindrical boundary. Inside this boundary, the air is relatively calm, creating the eye. The eye and the eye wall have drastically different characteristics. The eye features the lowest barometric pressure, light winds, and sometimes even clear blue skies. The air inside the eye is actually slowly sinking and warming due to compression. Surrounding this calm center is the eye wall. This is the most violent region of the entire cyclone. It consists of a towering ring of deep convection, producing the heaviest rainfall and the absolute fastest maximum sustained winds in the storm. In its mature stage, the cyclone develops a central dense overcast, or CDO. This is a massive shield of cirrus clouds, mostly made of ice crystals, that spreads out from the top of the eye wall thunderstorms. Below the shield, convection is organized into long, narrow rain bands that spiral into the center. These spiral bands are packed with cumulonimbus clouds that deliver intense, heavy rainfall, while the outer periphery features nimbostratus clouds that bring prolonged, steady rain. Tropical cyclones breed in specific regions, almost always coinciding with warm ocean currents. The Western Pacific sees the highest number of these storms globally. Other major breeding grounds include the Western Atlantic and Caribbean, the Eastern Pacific, the Bay of Bengal and Arabian Sea in the Indian Ocean, the waters around Madagascar and the Southeast African coast, and off the coast of Northwest Australia. Interestingly, the Northern Hemisphere experiences about twice as many tropical cyclones as the Southern Hemisphere. Why? First, the Northern Hemisphere has less ocean area, allowing the water to heat up faster and reach higher surface temperatures. Second, the thermal equator generally sits north of the geographic equator, keeping warm currents there longer. Finally, massive river systems in the northern hemisphere dump huge amounts of fresh water into the oceans, increasing stratification and keeping surface waters warm. While we focus on the tropics, there is a unique phenomenon called metacanes, cyclones that form over the Mediterranean Sea. Although they occur in colder waters and typically during the fall or winter, they share many features with tropical cyclones. Metacanes have a symmetric structure, a warm core, a clearly visible eye, and winds that reach tropical storm strength. However, they are usually smaller in diameter and have lower maximum wind speeds than true tropical cyclones. Depending on where you are in the world, these massive storms go by different names, even though the meteorology is the same. In the Indian Ocean, they are simply called cyclones. In the Atlantic and Eastern Pacific, they are known as hurricanes. In the Western Pacific, around Asia, they are called typhoons. And historically, in Western Australia, they have been referred to as willy-willies. The path a tropical cyclone takes is heavily influenced by global wind patterns and the Coriolis force. They generally follow a parabolic path. They start by moving westward, driven by the tropical easterly trade winds. Around 20 degrees latitude, the increasing Coriolis force deflects them poleward. By the time they reach 30 degrees latitude, they get caught in the prevailing westerly winds and are steered eastward, eventually losing energy over cooler waters or due to high wind shear. Within the cyclone itself, wind speeds are not uniform. The strongest winds are consistently found on the right side of the storm, relative to its direction of motion. This is because the forward motion of the entire storm system adds to the speed of the swirling winds on that side. For example, if a storm with 145 km/h winds is moving forward at 16 km/h, the right side will experience 160 km/h winds, while the left side will only feel 130. To categorize the intensity of these storms, different scales are used. Globally, the Saffir-Simpson hurricane wind scale is common, ranking storms from Category 1, with minimal damage, to Category 5, which brings catastrophic destruction, with winds over 250 km/h. In India, the Meteorological Department uses its own scale, classifying systems from a basic depression all the way up to a supercyclonic storm, which features winds exceeding 222 km/h. The damage from tropical cyclones comes from three main sources. First, torrential rainfall can cause massive inland flooding, sometimes dropping up to 250 centimeters of rain. Second, the extreme winds can uproot trees and completely destroy infrastructure. But the most deadly element is the storm surge. This is an abnormal rise in sea level pushed toward the shore by the storm's winds. It inundates coastal areas, causing massive loss of life and ruining agricultural land with saltwater. History shows just how devastating these storm surges can be. The 1970 Bola cyclone in the Bay of Bengal caused over 500,000 fatalities, primarily due to the surge over low-lying deltas. The 1999 Odisha supercyclone was the strongest recorded in the region, with winds hitting 260 km/h. In India, the east coast states like Andhra Pradesh, Odisha, and West Bengal are highly vulnerable, with Gujarat being the most at risk on the west coast, particularly during May and the post-monsoon months of October and November. Despite their destructive nature, tropical cyclones do have positive ecological effects. They act as a global pressure valve, regulating ocean temperatures and maintaining the heat balance necessary for marine ecosystems. They bring crucial rainfall to parched, arid, and rain-shadow regions. The churning waters break up harmful algal blooms, known as red tides. They also pick up sand and nutrients to replenish barrier islands, and their massive winds disperse seeds far inland, aiding in forest regrowth. Why do we name cyclones? Because storms can last for weeks and multiple storms can exist simultaneously, naming them reduces confusion and speeds up communication. In the northern Indian Ocean, the naming process is managed by the IMD. 8 member countries contribute lists of names, which are used sequentially. Unlike the Atlantic, where names alternate by gender alphabetically, the Indian Ocean names are gender-neutral and rotate through the contributing countries. Recently, we are seeing alarming changes in cyclone patterns in the Indian Ocean. There is a noticeable increase in high-intensity storms, and they are forming in off-season months like January. This is largely driven by global warming. The South Indian Ocean, which used to average 26.5 degrees, is now seeing temperatures as high as 32 degrees. Furthermore, phenomena like El Niño Modoki are creating favorable convergence over the Arabian Sea, leading to an unprecedented number of severe cyclones there. Occasionally, unique multi-storm events occur. Twin cyclones happen when a pair of storms form simultaneously on opposite sides of the equator, spinning in opposite directions, like cyclones Asani and Kareem in 2022. Another fascinating phenomenon is the Fujiwara effect. This occurs when two cyclones form in the same region and pass close to each other. They begin to orbit around a common center, and depending on their relative strengths, they may eventually merge into one massive storm. A major driver of these twin cyclones and overall cyclogenesis is the Madden-Julian Oscillation, or MJO. Unlike El Niño, which is stationary, the MJO is an eastward-moving band of thunderstorms in the tropics that circles the globe every 30 to 60 days. During its enhanced convective phase, it creates massive low-level westerly wind bursts. When these westerlies meet the standard easterly trade winds, they create intense rotation, providing the perfect environment for tropical cyclones to be born. To protect lives, the Indian Meteorological Department uses a strict 4-stage warning system. It starts with a pre-cyclone watch issued 72 hours in advance. Next is the yellow cyclone alert, issued 48 hours before bad weather, when the storm is over 500 kilometers away. Then comes the orange cyclone warning at 24 hours, providing specific landfall estimates. Finally, the red post-landfall outlook is issued 12 hours before impact, detailing the exact time, place, and expected severity of the strike. To wrap up, remember that tropical cyclones are massive heat engines that require ocean temperatures above 27 degrees Celsius and the Coriolis force to spin. They develop through distinct stages, culminating in a violent eye wall surrounding a calm eye. Crucially, global warming is altering these patterns, making storms more frequent and intense, particularly in the Arabian Sea. Understanding their mechanics and utilizing advanced warning systems remains our best defense against their devastating impacts.